Hi, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development in Grasshopper. This is going to be the third video in this mini series, Dynamic Simulation Components, where in the previous two we've done the point that bounces off a region, and we have modeled also a pendulum that is subject to gravity and to elastic forces. This exercise, the third one, is going to be super similar to the pendulum one. We're also going to be working with gravity, and we're also going to be working with elastic forces. But the goal of this one is to model the deformation of some kind of elastic rope or chain or linear element that is deforming under its own weight. And it's going to look something like this. So it's going to look like two anchor points with a line between them and then some forces that are affecting the particles that we're using to model this system, And we have things such as mass that we can control, the stiffness of the spring, but at the same time, we can also, as we've done in previous example, we can modify the system in real time, and then the simulation will try to adapt over time and reach some kind of equilibrium through the combination of all the forces and the friction that we have introduced in the system. All right. This is also a great example for doing form finding. If you are a fan of, like, for example, Gaudi's work and how he used chain models for form finding, this is at the core of how to simulate these processes computationally and do a similar work to what Antonio Gaudí used to do, like in the Sagrada Familia. This is going to be very similar to the second example that we did in this mini series. It's just going to involve more nodes, more velocities, and handling, just instead of one particle, managing a collection of particles that form our simulation. Okay, but it's going to be super similar in spirit and very easy and a lot of fun to implement. Okay. All right, so with this, let's get hands-on and let's go to the whiteboard and let's first think through the problem on how we're going to model this thing, okay? All right, let's get hands-on. Okay, so the way we're going to do this is going to be very simple. What we want to model is the elastic deformation that a chain made out of springs, for example, would suffer under gravity. And the way we're going to do that is that we have, for example, 2 points, and what we want to model is the curvature that it will get over time as it bounces off and it ends up relaxing and reaching equilibrium. When it comes to physics simulations, because we're using computers to do these simulations, we can't really model the perfect continuity that a rope or like a continuous element would have sagging under its own weight. That is not really a possibility. So what we do actually in the real world is that what we model is the initial system. We assimilate that the system is made out of a discrete amount of particles. So if we start with a straight line between the 2 points, we basically subdivide this in however many points we want to use to simulate this element. And the more points, the more perfect or the more accurate will be the curvature of the element, but it will also take more computational cycles. And then what we do is, once we have those, we calculate at every iteration of the simulation how these nodes are moving in three-dimensional space, so that we make this simulation evolve. Now, when it comes to designing the simulation of each one of those nodes, we actually use very similar techniques to what we have done in the previous examples. So for every node, what I do is basically think, well, which are the forces that are acting on any of the nodes of my rope, for example, or my chain. And that is going to be, for example, one of them will be gravity. So all the nodes will be affected by some kind of gravity. And then the other one will be that because each node is connected to the nearby nodes or the neighboring nodes, we will have, if we model this with in an elastic way with springs, we will have some kind of spring elasticity from the node that is on the left pulling back to that side, and we will also have some kind of elasticity from the spring that is on the other side, and it's pulling, and basically the node is being pulled between the two springs, correct? If we add them all together, we will have some kind of resultant force, which is the one that is actually acting on the system. And if we just do this every iteration for all the nodes, then we will basically be able to move them around and design what is the final location that they will achieve after they've been bouncing and moving around for a certain amount of time. Okay, we will also introduce friction to make sure that the system reaches equilibrium. We will do this for all the nodes except for the ones that are considered anchors and that are considered immutable, that don't move in three-dimensional space. Okay. All right, so it's going to take a little bit more of code than in the previous examples, but conceptually it's actually pretty much the same. All right, so let's take a look at how to actually do that. Okay, let's start. So as I have done before, I have gone ahead and dropped here a C# component that has a bunch of inputs. So I'm going to have a Boolean that is going to be resetting the simulation. I have the 2 points that I'm bringing in from Rhino, which are going to be the anchors that I'm going to be using in my system, anchor 0 and anchor 1. And then what I'm going to do as well is that I have added a new input, which is the amount of nodes that my system is going to have. So that is going to be, as I showed in the example before, how many particles am I going to be modeling? All right, and this will make the simulation faster or slower, but also more refined or less refined. Something that we have been doing before, we have added the radius of the ball in the previous simulations, but we haven't actually used that radius as a way of saying that if I have more mass, then gravity is going to pull this object more to the ground. Okay, so I need to remember to do this in this example. So I have added mass, the mass of the particles, as an input to the system as well. We have gravity, which is a vector, and we also have stiffness and frictions, which are just two numbers that are going to affect the elasticity of the rope, but also friction is going to affect how much the system is going to damp down over time. Okay. And that's about it. So we're going to go ahead. I have created outputs for the points in the simulation, so the nodes. V is going to be the velocities that I'm also going to be plotting in real time. And C is going to be like a shape that I'm going to create through the inputs. All right. I'm going to drop geometry components so that we can see all of these. And I'm also going to drop here a vector display so that we can see whenever we get these, we can see the vectors displayed here on the screen. All right. Beautiful. So what are we going to do then? Well, first of all, what I would like to do is I would like to go ahead and define what is going to be part of my algorithm and what is going to be what are going to be my outputs. Okay, I am just like very OCD about that, as you probably already know. And then the next thing I'm going to do is I would like to make sure that I have here in my custom additional code, I have variables that define what is persistent, what I need to keep between iterations of my simulation so that I can have those values available across simulations and change them over time. In the previous examples, I have done 1 point, like location, and I have done 1 velocity, the current velocity. But because now I'm modeling a multi-particle system, it's not just one. In this case, I cannot use just one element. So what I will need to do is I will need to create lists of particles and lists of velocities, each one corresponding each one of those particles. I could do this with classes, so I could create a node class, I could create a force class and blah, blah, blah. And that would actually be an amazing exercise, which maybe we will do in the future because I've gotten a lot of requests to do a dedicated playlist on physics simulation. So that may happen at some point, but it's not going to happen anytime soon, right? Okay. But if it will, maybe it will pop up as a card somewhere here, etc., etc. But I'm going to do it like a little bit raw. So I'm going to just handle all of these elements manually independently as opposed to creating classes for it. Okay. So what I'm going to do is I'm going to create a list of point 3D objects, which is going to be the nodes. And I'm going to not initialize it, or I could initialize it to empty. That would also work. All right. And then I'm going to create also a list of vector 3D objects, which are going to be the velocities. And I'm also going to initialize this to empty. Why not? Okay, cool. So I'm going to maintain always two lists, one of nodes and one of corresponding velocities for each one of those nodes. Then when we reset the simulation, as we have seen in previous examples, what I would like to do is I would like to make sure that I don't have anything on this list. So I'm going to say nodes clear, okay, and velocities clear. So I'm going to start from scratch. All right, beautiful. But because I start from scratch, something that I would need to do as well is I would need to say, well, given how many nodes I have on my system, what I would like to do is I would like to create an initial set of particles that corresponds to this amount of nodes, and then use those as the starting points of my simulation. So here, when I reset the algorithm, what I will need to do is I will need to figure out how to create a set of points that are equally distributed between the anchor 0 and anchor 1. All right? There are multiple ways to do that. So we could just do it manually. We could calculate the coordinates and do a for loop, etc., etc. I'm just perhaps going to use a more convoluted way, which is I'm going to be using Rhino Common, and I'm going to be dividing that line, and I'm going to be dividing into a set amount of segments. Okay, but we could do this manually in a very easy way. We could just calculate the difference of, maybe that's actually a good exercise to do. So maybe I could do that, but I'm going to stick to random. So what I'm going to do is, first of all, I'm going to create a line that which is going to be a new line from anchor 0 to anchor 1. All right. Then I would like to subdivide that line into an amount of points. The problem is that lines in Rhino don't have a subdivision method. So what I need to do first is I need to convert it. This is the convoluted way. Line curve, I need to convert it to a nerves curve. So I need to say line dot and then to nerves curve. Basically, it's the same object, but internally, instead of being represented as a line, which is just the two ends, it's a nerves curve. And because it's a nerves curve now, I can take that curve and divide it by an amount of points. So you know that line curve, because it's a curve, now I can say divide by count, and I can design how many elements, how many segments I want to divide this by. So divide by count is going to say how many segments do you want to divide. Remember that my input says how many nodes, and here I've been asked how many segments. So if I divide a curve into two segments, I will get 3 nodes. If I divide a curve into 3 segments, I get 4 nodes. So here what I need to do is I need to divide by the amount of nodes minus 1. All right. And I do want to include my endpoints. All right. And if I do this, I will be able to see that what this function is giving me in return is actually not the points, but is an array of doubles. So let me show that again. It's an array of doubles. This is because the function is designed to give you the parameters as values at which those divisions will happen. However, thankfully there's an overload that already gives me, as well as part of an out parameter, it gives me the actual points on those parameters, so that I don't have to now go with a for loop and each one of the parameters and like extract that point from the curve. So what I can say is, oh, I want this to go into a variable which is going to be an array of 3D points called PTS, and before I run this code, I need to create that variable, an array of 3D points called PTS. Okay, beautiful. And since I'm not going to be using the parameters that this function returns, then I don't need to actually store that in any variable. This is what I'm interested in, these points. Then, okay, so now I have all those points. So now I can say nodes, can you add a range? And that's going to be all these points that I just generated. To make sure that this is working, what I'm going to do is I'm going to now go to the outputs and say the outputs has to be all those nodes. And if I press reset, you can see that I got all the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so this is correct. I got all my points here, all my nodes, and I can start simulating those nodes. I can start simulating those nodes now. All right. Similarly, for the velocities, remember we need to initialize those velocities. So if I have 10 nodes, what I will need to do is I will need to create 10 velocities which start at 0. So what I'm going to do is I'm going to say for int I equals 0, I is less than node count and I plus plus, I plus plus. What I'm going to do is I'm going to say to the velocities list, I'm going to add a new vector that is going to be a 0 vector. So I could do this, or I could just say a new vector 3D, which is 0, 0, and 0. Both work the exact same thing. Okay? And then also for the sake of visualization, I'm going to output that through the output. So now I have velocities. I'm going to reset this, and you can see that I have all these 0 vectors, and that's why they're not showing here because there's 0 vectors, but they are. Okay? Beautiful. So this is great. And I think at this point, we are ready to start the simulation. What are we going to do? Well, just like we did in the previous examples, the only thing that we need to do is we need to go through each one of these nodes, each one of the points. And for each point, what I need to do is I need to calculate what is the gravity for that point, what is the spring for with the node on the left, what is the spring with the node on the right, and then add them together and add them to the current velocity, apply some friction, etc., etc. All right. Before I do that, I'm going to turn on my light, which just went off. Great, my face is all shiny and bright again now. Okay, also before we forget, I'm going to, here on the outputs, I'm going to create a polyline, which is going to be, I'm going to call it I don't know, the chain, which is going to be a new polyline with all the nodes as inputs. And actually, I can just output that directly over C. All right. And then, oh, this is not working. C is a new polyline. Okay, so I'll take a look at why this is not working at some point. Sure. Okay. All right, beautiful. So now inside of the actual simulation, so we need to start simulating. All right. Simulate forces for each node. So what I'm going to do is I'm going to go with a for loop and I'm going to say int I equals 0, I is less than nodes dot count, and I plus plus. All right. And this is great, but this is not going to work. Okay. Because think about this. In this case, due to how I have arranged my simulation, it turns out that the points at the ends, the first point and the last point of my list of nodes, are anchors, and those points should not go anywhere or should not move. Therefore, I should probably not run a simulation that is going to look at all the nodes from 0 to node count -1 or whatever this one is. Okay, so what I will need to do is I will need to start with node in position number 1 and end with node in position count -1, which will be this one. So if that's true, then I need to modify my for loop and say, instead of starting at 0, I'm going to start at 1. And instead of ending at count, I'm going to end at count -1. And just because I want to be very verbose, I'm going to say point 3D P or N is going to be equal to, from the list of nodes, element in position number I. And vector 3D V is going to be nodes, velocities in position number I. Okay? Beautiful. So now that we have this, I can use this to read information and to start calculating. Let's start calculating all the forces. So for example, vector 3D, gravity force is going to be equal to gravity. Okay. However, this is what they didn't do before. Gravity is typically multiplied by the mass because objects that are heavier have more gravity than objects that are not. Okay, so this is something that we didn't do in the previous exercises, and that's why we calculated independently. All right, now let's calculate the spring force with the previous node. Okay, so for example, let's say vector um, previous spring, the spring with the previous node. So that's going to be equal to minus the stiffness, as we saw in the previous example, and then the distance between this node and the previous node. So this node is n, so this point, and then the one on the left is going to be, from the list of nodes, is going to be the one that is in position I minus 1. All right? This is a point. This is another point. When I subtract them, I get a vector. So that the whole thing is a vector that is scaled by the stiffness. Now, vector 3D next spring, same thing, is going to be equal to minus stiffness times the distance between the node that we're looking at right now and the one that is next on the list. So the one to the right, if you will. So that's going to be n minus nodes I plus 1. So the one that is right next. And this is also the reason, because we're looking at the previous one and we're looking at the last one, this is also the reason why we need to start with 1 and we need to end 1 unit before, because then if we don't do this, we will not have nodes on the sides to compare with. All right? Beautiful. So let's aggregate all the forces. All right, so let's say vector 3D total force is going to be equal to gravity force plus previous spring plus next spring. So now we have the total. All right, now let's update velocity with this value. So we're going to say V is going to be increased by the total force. Now let's add some friction. We saw this before in the previous example. V is going to be multiplied by some friction. All right. And then let's update the location of the node. So N is going to be increased by the value of V, this velocity that we just modified. All right. And now what we're going to do is that this would not be enough, because it just so happens that this is a very technical thing. Point 3Ds and vector 3Ds are structs, and when we read them from a list, we read them by value, not by reference. So all the changes that we have done to N and V are only going to be from this are going to be only affecting these two local variables, N and V, but are not going to be affecting the actual node on the list and the actual velocity on the list. So what I need to do now is I need to update values on the original lists. So what I need to remember is I need to say nodes in position I is going to be equal to this new modified value that I have now, which is N. And for velocities in position Y, I also need to overwrite that and say that I have updated this value with this variable that I've computed that is called V. All right? And I think with that, we should be ready to go. Let's actually see how this would work if I only had stiffness, if I only have had the gravity. So right now this is not working. Previous spring that all right. Okay, so let's just see the whole thing working, and that's it. So oops. Okay, so this is going to work, and then I'm going to reset this, And then I'm going to put a trigger in here, and we're going to simulate this at intervals of 200. Whoa, this is going very far. So let's reduce the mass. All right. Oops. So let's reduce the mass, and let's perhaps what? And let's reduce the stiffness. And okay, and let's create a chain between these two elements. Oh, this should be, I'm going to move this back to 0. I'm going to move, I'm going to displace this to 0. No. Projected point. Ah, okay, and here what we're going to do is we're going to create a new polyline. C equals new polyline with all the nodes. Okay, just for visualization. And I'm going to start this, and you can see how the nodes start sagging, and at some point they reach some kind of equilibrium. I'm going to lower the mass also a little more, because perhaps it's a little too much. You see how they're dragging, and it's forming this chain, and we can see the velocity vectors dragging the chain. And let me just crank this up. All right. Ooh. Now it's bouncing back up, and I think it's uneven because this point is higher in 3D space. But you can see, and if I were to make the thing more stiff, you can see it starts bouncing off. Oh, you see how it's stiffer now? Oh my God. Oh, this is something that happens very often with simulations. They become unstable because there's some kind of offset. Some of the forces are stronger than the others, and then it cannot reach equilibrium. This happens a lot, actually. The stiffness is just stronger than the weight of the elements in this case. So, all right. So this is great, except for one tiny detail that I want to improve here. What's nice about this is that we can use this for dynamic form finding. All right. So if we had a chain that we wanted to model, we could say, if we want to use this for design, I may want to say, well, this is too high here. So I wonder if I move this over here, if the chain will become more taut or like less high here. But the problem is that I just moved this, but the simulation stays as it is. It stays as it is, and it doesn't update this anchor to this new position. Why is this the case? This would only happen if I restarted the simulation again, but not if I move it while the simulation is happening. And that is because if you think of the code, the only time that we have used the anchor points, anchor 0 and anchor 1, has been when we created the new line that we then subdivided, etc., to create the nodes. But after that, every time we simulate, unless we reset, we're not taking into consideration these new anchors. So something that we can do is, just to make sure that we're listening to changes in the simulation, something that we can do is we can say here, let me just update the location of the anchors every time I simulate this system, just in case one of the inputs, just in case the user has been moving the point around. So what I can say is, I can say node 0 has to be equal to anchor 0, and um, nodes dot count minus 1. So the last node has to be equal to anchor 1. So I basically override whatever values I calculated at the beginning of the simulation. I override them every time to make sure that I account for possible changes in the location vectors. And if I do that, I'm going to start this. This reaches some kind of equilibrium, etc., etc. But now I'm going to take this and I'm going to move it. And how cool is this? Huh? How cool is that the simulation is now, the springs are like moving in 3D space and like reorienting, and the chain is kind of You see it, this side sway that it heads between, because oh, how cool is this, right? And I do this, and look at how all the springs are like moving around and trying to reach equilibrium, right? I mean, isn't this the coolest thing ever? Seriously. This is so cool. I love this. I just cannot express it enough. All right, beautiful. Okay, so with that, I think this is where I wanted to finish this exercise. Is this what I wanted to do? And yes, so this is the end of where I wanted to get. So this is the last of the 3 videos in this mini series, how to create dynamic simulation in components. The first one was bouncing, making a ball bounce off some boundary. The second one was to model a pendulum. And this video has been to model an elastic chain, deforming under its own weight. Okay, so I hope this was fun. I hope you learned some particle physics simulation. I also hope you learned how to use persistent data as a way to mimic a continuous execution in Grasshopper components. And then maybe this is the door for you to create your own Kangaroo plugin or your own dynamic simulations, and to use this for form finding, etc., etc. This is endless. It's like a really, really cool, really cool thing. Okay. Beautiful. So thank you very much for being here. And with this, we're going to move on to the next videos in this series, Advanced Development in Grasshopper. So thank you very much. And if you liked what you saw, maybe like this video, hit the subscribe button, hit the bell button to get notifications when we go live, when we post new videos, etc., etc. See you in the next videos. Bye bye. Thank you.